So these are the lecture problems for Chapter 9. Take a second to read the problem. So here we have a crane that is lifting an object and it's got a counterweight. I'm drawing the upper cross beam of the crane here, and what I'm going to do is I'm going to draw the Freebody diagram for this guy. It's being supported by the tower, so there's going to be some force of the tower in the upwards direction. We're going to have the mass of the weight that you're lifting multiplied by gravity on the far end. We know that this distance right here, I'm going to call that lowercase d, is 7.7 meters. And we have a counterweight that is movable, adjustable in terms of distance. So we're going to have the mass of the counterweight multiplied by gravity, and this is going to be a variable distance. I'm going to call that distance x, and it's variable up to an upper limit of 3.4 meters. So this crane is in equilibrium. I can write all of Newton's laws for it, as well as the second law in terms of rotation. I'm going to go ahead and apply that one. I'm going to say sum of the torques must be equal to 0. This crane is in equilibrium. I'm going to choose my point to sum all the torques about to be right here. The reason why I'm doing that is because I don't know the support force of the tower, and I can eliminate it simply by choosing that as my pivot point, because the distance to the pivot point is going to be equal to 0. So here I have the counterweight. It's going to rotate this guy in the counterclockwise or positive direction. So I'm going to have the weight of the counterweight in the positive direction multiplied by the distance, so force multiplied by distance. And then in the negative or clockwise direction, I'm going to have the mass of the weight multiplied by gravity multiplied by that distance d right there to get my torque. Again, torque is force multiplied by distance. So I can rewrite this guy as mass of the counterweight, gravity, distance, mass of the weight, gravity, distance. I can go ahead, I can cancel out my gravities, and I can solve for this distance for the counterweight. Must be the mass of the weight divided by the mass of the counterweight multiplied by that distance d. So go ahead and plug these guys in, and I come up with 2800 divided by 9500 multiplied by 7.7. So my position is going to be equal to 2.3 meters, position of the counterweight. For part B, we're actually going to start this guy totally the same. We're going to write all of the torques about the pivot point there. Only this time we're going to know that that distance x is going to be the maximum that it can possibly be, which is 3.4 meters. And now I'm solving for this mass right there. So I can erase this guy as well. So now what I end up with is mass of the counterweight multiplied by gravity multiplied by x max. That's going to be equal to mass of the object that you're trying to lift. This is going to be some maximum value multiplied by gravity multiplied by that distance. Again, gravity is going to cancel out, and we're solving for the maximum weight that we can lift now. So mass weight max is going to be equal to mass of the counterweight multiplied by its maximum position. Divide that by the distance. So mass of the counterweight is going to be 9500. The maximum distance that it can be extended is going to be 3.4 meters. Divide that by 7.7 meters, and we're going to end up with about 4,200 kilograms. Okay, take a second to read the problem here. First thing I want to do is draw my free body diagram. I'll just draw it right on their particular diagram here. Draw all the forces that are acting on this guy. I know that the traffic light has some mass multiplied by gravity. Know that this guy is going to be giving some tensional force. Now the pole is uniform and it also has mass, so what that means is all of the mass is going to act like it occurs at the center of it. So we're going to now have to worry about the mass of this pole. We'll call that little mass multiplied by gravity. And lastly, I know at point A this hinge is going to be giving some forces as well. Force A in the Y and force A in the X. And if I had to solve for these guys and I chose the directions wrong, the math would bear me out. I also can say I know that that 37-degree angle is also going to be the same as that angle right there. And I can say that this distance from A up until the center of mass is going to be half of the length, or L divided by 2. So kind of drawing or trying to, what I want to do is I want to look at the torques. So to do that I need to solve for my lever arms, starting with the tensional one right here. It acts along in this direction I'm drawing here in black. That makes a right angle with the point that goes through my pivot point just when it hits the pole. We know what that lever arm is. It's 3.8 meters. Similarly for the two masses, I'm just going to do the big mass right here. This force acts in that direction. I know that the length of this big long pole is going to be a capital L. So my lever arm over down here for the big mass is simply going to be L multiplied by the cosine of theta, and for the little mass it's going to be L over 2 cosine of theta. Those are going to be my lever arms. So I go ahead and I say this guy is in equilibrium. I'm going to write Newton's second law for torques and say all these torques must add up to be 0. Where should I do this about? I don't know FAX and I don't know FAY, so I'm going to choose that to be my pivot point and calculate all the torques around that just to make my life easier. I'm not going to solve for those guys if I don't have to. So working my way up the pole, the first force that I have is going to be little mass multiplied by gravity, and it's going to act at a lever arm of L over 2 cosine of theta, knowing that torques are forces multiplied by their lever arm. So here I'm going to have mass times gravity, and then the lever arm of L cosine theta, or L over 2 cosine theta. Now for the direction, that is going to be a clockwise torque, so I'm going to call counterclockwise positive. That's a negative torque. Same thing for the big mass, gravity, and then L cosine of theta. And lastly I have my tensional force, which is going to produce a positive torque. So I got my tensional force and my lever arm. I'm just going to call this H for just a second right here. It's going to be 3.8 meters. Torque multiplied by H. Now I simply solve for my tensional force right here. I move the other two guys to the other side and I divide both sides by H, and I'm left with the tensional force is going to be mass multiplied by gravity, L divided by 2 cosine of theta, plus big mass, gravity, L cosine theta, divide all that guy by the height. And I can actually simplify this quite a bit by saying this is going to be little mass divided by 2 plus big mass, and then pull out the LG cosine theta, divided by height. Go ahead and I plug all of those guys in. My tensional force is going to be 6 kilograms plus 21.5 kilograms multiplied by the length, 7.2, 9.8, cosine the angle 37, divide all that guy by 3.8, and I get my tensional force to be equal to 407.8 newtons. Now to solve for the forces that are involved, unfortunately I have to do that. I can go ahead and simply say, okay, let me write Newton's second law. What is the sum of the forces in the x direction here? In the x direction, all these forces must add up to be 0. So in the x direction I have force A in the x direction, and then tension in the opposite direction. So my force AX is simply going to be equal to the tensional force, which I've already solved for in the last little bit, so 407 newtons. Now in the y direction, I do the same thing. Some of the forces in the y direction must be equal to 0. This guy is in equilibrium, and I'm going to have the force A in the y direction, and that's up, or so I called it, so I'm going to say that's positive. And then in the downwards direction I have the little mass multiplied by gravity and the big mass multiplied by gravity. So my force A in the y direction is simply going to be the little mass plus the big mass multiplied by gravity, or 33.5. I simply added those guys together, multiplied by 9.8, and I'll get 328 newtons. So that's going to be my force in the y direction. So last but not least, I have a Young's modulus column, where here I have a marble column that is supporting some big mass right here. Asked to calculate the stress and the strain. We know that the stress is going to be the force divided by the area, and the force is going to be the mass multiplied by gravity. Divide that guy by area, so 25,000 kilograms multiplied by 9.8 meters per second squared. Cross-sectional area of that guy is going to be 1.4 square meters, and turns out that my stress is going to be 175,000 newtons per square meter. For my strain, I know that the strain is going to be related to the stress, and Young's modulus, the book used an E right there, so I'll do the same even though I'm used to a Y. We can look up what Young's modulus is for marble. We'll do that in the book right there, and you can find that it's going to be 50 times 10 to the 9th newtons per meter squared. So the stress is simply going to be, the strain is going to be the stress, 175,000, divided by Young's modulus, which is going to be 50 times 10 to the 9th newtons per meter squared. And we're going to come up with the strain being 3.5 times 10 to the minus 6. And note that there are no units associated with that, because the units of newtons per meter squared canceled out with the units of newtons per meter squared here. We could also, now that we know the strain, we could take this a step further and say if we knew what the length of this column was, how much does the length change by when it bears that load, and so on and so forth.